Right, I'm going to go through ecological sampling. I'm Dr. Ellis, if I don't teach you. So why do we do ecological sampling? So I've got two things here. It might be to find out how much is in a defined area, normally to track change over time. So if I'm a conservationist, I might want to make sure that what efforts I'm putting in to protect an area are having an impact, and therefore I might go to a certain area every year, measure what's there, and go back year on year on year to track what's happening to what is there. Again, it's pointless, doing a one-off what's there is pointless. You have to keep going back to get more data on how things have changed. Okay. And if you're doing that, then you do something called random sampling. Okay. The other one is, it says to measure distribution over a defined area, normally to investigate why the organism is spread in this way. And that's when you perform a transect. So I might be interested in, how does pollution from a road affect the distribution of a plant species in a field? Okay. And then you tend to also measure, so you kind of measure what's there biologically, and then you might want to take some probes around to measure the CO2 in the air or the SO2 in the air or the pH of the soil. You might measure abiotic factors as well that go along with that. Okay, so you just need to be able to, in the exam, write a 6 marker on random sampling or a 6 marker on a transect. What you must be very wary of is if you write a transect answer to a random sampling question, then you can get properly scuppered. Okay, so that's what we're going to do today, is just make sure that we know the difference between random sampling and a transect. Is this the same as GCSE? Yes, it couldn't be more straightforward. People never learn it though. I always think this is like biochemical tests. It's too easy to learn Benedict's and Burette tests. Therefore in exams people get that wrong for fun. And the same goes with this. Sampling technique questions, people are asked to write a method and you tend to get 2 out of 6 on average. Yeah, very poorly answered. So again, it's not hard, and that's what we'll hopefully do here, is just practice it and make sure that we get it right. We just need to be a bit more careful when it comes to accuracy, reliability, and bias. We just need to be a bit more specific at A level. But otherwise, a good GCSE answer will get most of the marks anyway. Okay, so here's this table. Again, I just listened to this first, but I'd be making your own little copy of this into your notes, adding a few bits because I'll be going through some other slides just to elaborate in a few places. So I've got 2 problems at the top. How many daisies are flowering in the field? And does the distance from the road affect the number of flowering daisies? So the technique I use for how many is there is random sampling. Note that these are about plants that aren't moving. There is a third technique that we use to estimate the number of things that move around, which we're going to do separately. And then, how does something change? So if I'm dealing with distribution, it's transect. In terms of equipment, it's the same equipment needed. You need a suitable quadrat, that's a frame of known area, 2 tape measures and a random number table. So firstly, free of bias. Well, this is where, again, we need to place the quadrat randomly. We never throw a quadrat. So we do that by placing tape measures along the sides of the sample area, like an X and Y axis. I don't know which way round it will be when you see the video. Sometimes described as making a grid. Sometimes you can peg out an entire grid out of string to actually make physical little sample areas. But crucially, we pick coordinates to place the quadrat at from a random number table. Avoid saying random number generator. Ecologists, you're in a field, you haven't got your computer, you have a little booklet of random numbers that you pull out of your top pocket in your Kaggle, and then you look up where you're going to sample. So it might say 7, 8, I go meter 7 and 8 meters up, and that's where I place my quadrat, at those coordinates. For a transect, it's, this is where you place a tape measure along the starting edge of the sample area. So if I've got a road and I want to see if it changes from that road, I'll put it parallel to the road to pick a random starting point. Okay, again, I'll use a random number table. I'll get that into my answer, and then you're going to sample every 5 meters. So it's systematically sampled. It doesn't have to be 5 meters. I've just made that number up, but I'm not going to sample at random places after that. I just have a random starting point and then you measure at set distances. Again, I'll show you a summary diagram at the end. Accuracy is all about getting close to the true value. and therefore that's when you use a suitable quadrat, and we use a counting or measuring rule. I'll go through that on another slide. But what I count in my quadrat needs to be the same as what you would count in the same quadrat. I can't say, oh, there's 15 daisies, and then you come along and say, no, there's 12 daisies. So that's not accurate. One of us is correct there, and one of us isn't correct. So we need a way of making sure that we get the same answer every time. Okay. And yeah, that's the same on both because you're using a quadrat in both. Reliability. This is, are you confident in the answer? So again, if you're ever going to quote a number, put 20. Yeah, you'd have to sample at least 20 different areas with your quadrat, minimum. And then we're going to use a running mean to decide if more data is required. Again, I'll show you another slide where we go through a running mean. But yeah, don't put 10 because we have 10 fingers. Years ago, 15 was the preferred answer. And then a couple of years ago, they suddenly said 20 minimum. So yeah, put 20, put 50. Yeah, as long as it's a high number. It's it's crucially different to doing a experiment in physics where you're rolling a ball down a ramp. 3 sets of data is enough there to spot an anomaly because it's all very predictable. Measuring daisies in a field when there's trees over there and a football pitch over there, you need to get lots of data. If you want a job where you're out a lot, in the sunshine or in the drizzle, and then you come back and you do your mathematical analysis, ecology is for you. And transects, yes, this is where you do a mean of parallel transects. So for it to be, if I just did one transect, that might not be representative of the entire area. I might be hitting a path that snakes down the field. So you have to do numerous transects and do a mean across. Again, I'll show you in a little picture in a second or two. Other information. The problem for the daisies is how many daisies are flowering in a field. And people tend to, they say about placing the quadrat, they count the number in the quadrat, then the better ones go on to say, then repeat that sampling process in 20 more different areas, or 19 more different areas, and then calculate a mean, and then they stop. They don't then say that you have to divide the area of the field by the area of the quadrat, effectively finding out how many quadrats fit into the field, and then times that by the mean number of plants in that quadrat. I haven't written that perfectly, but yeah, make sure you go back and read the question again to make sure that you've answered the full question. Again, people tend to do the complex and then don't say the obvious at the end. It happens for loads of things. Explain the effect of increasing temperature on the rate of photosynthesis. And they put all the detail down and don't say it increased. Yeah, there's an easy mark there. Transect, the other thing to remember, that you have to have a direction stated. I'm going to work from the road, perpendicular to the road at 90 degrees, therefore, down the field, away from the road. So a direction must be explicit in any method for performing a transect, because that's going to be if pollution stops the plants from growing near the road due to the heavy traffic. My data needs to show that I need to, because I could have come towards the road instead, in which case the numbers wouldn't match. So let's have a look at, I think, free of bias, nothing really changes. We're going to just do a little more on these yellow, green and purple. Is it great? So accuracy, suitable quadrat and counting rules. So let's look at this left-hand picture first. So this is a frame quadrat. And if I was counting the number of yellow flowering plants, or plants that are flowering at the time that have got a yellow flower, I've got a suitably sized quadrat here. Okay, if I was counting grass, blades of grass, it'd be a nightmare. Well, I'd therefore need a far smaller quadrat. So the size of the quadrat needs to be thought about. Yeah, but again, if it was bigger, I'd risk losing count of the number I've counted. If it was smaller and I was counting the yellow ones, then I get lots of zeros. So yeah, this is a suitably sized quadrat for counting the number of an individual plant. If those plants hit an edge, then I need a rule, a counting rule. So here's my red box here is the quadrat, the blue is the plant. How many would you count? 1, 2, 3, 4, 5, 6. I'd count 7. Okay. What I can't do is think, oh, now is this one more than half in or not? Because that would require a lot of judgment, and therefore I want to do it quickly. I want a fast measure so I can get more repeats. So we just have a rule, a blanket rule that is called the top left rule. If it touches the top or left, you count it. If it touches the bottom or right, you don't count it. So this top one here, it's touching the top. I count it. 1. I'll obviously count all those that are in. 2, 3, 4, 5, 6. That's touching the left. 7. That's touching the right. Don't count it. This 7 I would count. And if everyone follows that rule, everyone would get 7. If I just left it to people to decide, then people might discount those 2 or count those 2. So yeah, we have a counting rule. And when I write an answer, I just give a nod to the fact that I've thought about accuracy, because it might be a marking point. It might not be, but it should be. Okay, so yeah, I will make sure, place the quadrat at the coordinates and count the number accurately. You can even say photograph the area and then cross them off. Yeah, you can say double check the counting. So I count it, then my partner counts it, and then we decide if we are right or not. And if we don't agree, we do a double check, then a triple check kind of thing. But ecologists tend to use a top left rule. So I wouldn't just say use a top left rule. I would say use a top left rule for accuracy, so that yeah, so that it's clear what to count if it's touching the edge of a quadrat. Okay, so that works for a frame quadrat where I'm counting the number. Sometimes it's not appropriate to count the number. So here, this grey stuff is lichen. It's a part fungus, part algae. And I can't distinguish an individual fungal organism. It all kind of spreads out, same like moss as well. So here I'm using a gridded quadrat. It's small. You see my fingers. And then I just have to estimate the percentage cover. I've got 25 squares. It's a 5 by 5 grid. Each square is therefore 4%. And you will say, well, that's more than half full. Therefore, I count that as 4%, full, 4%, full, 4%, full, 4%. More than half full. Oof, God, that's a tricky one. Again, I'd probably call it and say yes. So say, of these squares, this one here, that one there, and that one here. I've got 3 that aren't classed as full, therefore it's 88% cover. Is that right? Anyway, all I'm doing is counting the number of squares that are half full or more, and I call it a full square. And hence I have to do that many times because I'm really estimating here. If I wanted more accuracy, I could have more divisions. I could, instead of having a 5 by 5 grid, I could have a 10 by 10 grid, and then I'll get to a higher level of there'd be greater resolution and therefore greater accuracy. But time is money. These are you would be a professional ecologist paid to sample an area. So yeah, it's better to count more areas than just do one area for a long time, because that one area might not be representative. It's a really good word, is representative. Why do I stir my coffee? So that I get every mouthful is a representative of 1 spoonful of coffee and 1 spoonful of sugar and this much milk. If I didn't stir it, it wouldn't be representative of that. It would be not sweet enough at the top, and it would be too sweet at the bottom. So yeah, representative, really good word. So yeah, so that's accuracy. Yeah. Again, you need to make sure you read a question. Is it asking you to count the number or the percentage cover? Because there's a different way of using both. Next is reliability. This is about being confident in the mean. So I've counted numbers of daisies in a quadrat. So on the x-axis is my sample number, and I've just plotted this just to illustrate what I mean. So the number 1 was my first quadrat, 2 was my second random quadrat, 3 the third, etc. And on the y-axis it says running mean. I know it's hard to read, but it's the mean so far. So in my first quadrat I counted 12. In my second quadrat I counted 6. 6 plus 12 is 18. 18 divided by 2 is 9. So it's 9 here. Okay, so all I'm doing is plotting the mean so far. It's called a running mean. And you can see how it's kind of like wobbly at the start, very wobbly, and it's getting less wobbly. And when this is my 15th sample, you do 20, and then but if I've done 15 and I've can I go home now, or do I need to do more? I'd probably do another one, and ideally it'd come between these two values. If it was 9.7 again, I'd probably stop. If it headed down here, I'd do more counting. So when the running mean stabilizes, it means that you can stop counting. So so here's my data. I'm only showing the first 7. That's the number I counted, and this is what I'm plotting, or this is what I'm monitoring to see is it stabilizing. So yeah, my third sample was 14, so that gave me a total of 32. 32 divided by 3 is 10.7. Therefore, that's why I plotted 10.7 here. Okay, so I wouldn't say plot the running mean. I would say do 20 samples when I'm randomly sampling, and then look at the running mean to decide if more should be done. Yeah, if the running mean is stabilized, I can stop. If it's still fluctuating wildly, then I wouldn't stop. If I had infinity on the x-axis, then I'd get to the true value because I would sample everything in the field. And therefore, yeah, the more you sample, the more it becomes the true value, the true mean. However, you don't have time to do every single part of a field, because then that's not sampling, that's just counting the entire field. And we have to sample. Okay, so that's reliability. So I'll kind of summarize this as 2 little diagrams, which I might, if I was doing my own notes, I'll probably do something similar. So this left-hand picture is random sampling. My red line is my tape measure. I put one on the x-axis and one on the y-axis, and then these little squares are my quadrats that I've randomly spread out. Yeah, so I'd go here first, then here, then I'm up here, then I'm back down here, and I'd be counting the number or the percentage cover in those areas, and then I get a running mean. Okay, so that's a transect. How much is there? Whereas here I've got my transect. I've done 4 transects here. So I've got my one along the south side of the field. So I get a random starting point. So this might be my first transect, my first random starting point. I lay my tape measure at 90 degrees to the first, or perpendicular, and I'm placing my quadrat at predetermined distances. And then I'll use the same technique that I would for over here, either percentage cover or count the number of individuals. Once I've got that data, I will then do another quadrat, another transect using my quadrats. So that this might be my second one, that might be my third one, and that might be my fourth one. In terms of reliability, I take a mean across. So when I was my first quadrats, I get a mean, then another one, and then another one, and so on. And I need to say that I'm heading from the south to the north. Okay, make it clear in my data. So that's sampling. Again, you'll have done it at GCSE. If we're in school, we would have, if we'd have gone to Bangor, we would have done it there, but that didn't go ahead. And if we're in school, we would have gone to our main school and done some kind of sampling in the field. But I'm not joking. Every year it's poorly answered, and no matter what we do, it's poorly answered. So maybe doing it like this might actually work, where we're not being distracted by being out in the sunshine, avoiding being stung by a bee. Here we're kind of thinking about it in a really kind of like boring, but probably a more exam-friendly way. Okay. Before I finish, I just want to do a few questions on that null hypothesis stuff. So I'll put some null hypotheses, so some what I think hypotheses here. Can we turn them into a null hypothesis? I'd pause it, see what you come up with, and I'll go through the answers now. So pause it now if you don't want to know the answers. So it says children under 16 are less likely to pass on the SARS-CoV-2 virus. So my null hypothesis would be age is not a significant factor in the transmission of the SARS virus, of this new SARS virus. Okay, if I disprove that, if it turned out that my data showed that under 16s were actually more likely, then I couldn't have a null hypothesis saying children under 16 are more likely. Yeah, I always have to go for not a it is not a factor. The bigger the arm span, the bigger the person's hand span. I might think that makes sense, but I would have to say there is no significant correlation between arm span and hand span. And you perform a Spearman's rank test, and you'll do a lesson on that later on. Caffeine increases heart rate. Caffeine has no significant impact on heart rate. I know for me, it speeds my heart rate up, but my partner, who has 18 coffees a day practically, I think she needs it to calm down. She gets stressed when she hasn't got caffeine. So I can't say caffeine has, by saying it has no significant impact, it means that if it decreased it, that would still be open to me to have my to be a valid result. Amylase for mammals works faster at 40 than 30. We just say there is no significant difference between how fast mammalian amylase works at 30 and 40. See how it says there is not, there is no, there is no, there is no. The surface area of gills is directly proportional to the size of fish. That makes sense. If you're a bigger fish, you've got more cells, you need more oxygen. And you just say there is no significant correlation between size of fish and surface area of gills, and therefore you'd measure both, and then you would reject the null hypothesis, and therefore you'd accept the fact that there is a significant difference between size of fish and surface area of gills. The only awkward one is this last one, which again in year 13 you do about genetics and heredity. It says when two cystic fibrosis carriers mate, if they're both heterozygous, you'd expect a 3-to-1 ratio of non-sufferers to suffer it in the offspring. Therefore, the null hypothesis is when two cystic fibrosis carriers mate, there is no significant difference from the expected 3-to-1 ratio. As in, this is nullifiable, hence why it's called a null hypothesis. This means I can compare what I have to what I expect it to be. So, for most null hypotheses, you'd say there is no, there is no, there is no, there is no, there is no. When you know that it should follow a certain ratio, then that becomes a null hypothesis. So you do have to have your brain switched on slightly. But in ecology, it's always going to be, if I think there's more nettles grow by the hedge than in the middle of the field, I say, there is no significant difference in the growth of nettles between the two areas of the field. So you assume that there's nothing every time, apart from when there's something to base it on, like a Mendelian ratio, and we hit this last one in year 13. So I'll stop there. Hopefully that was useful. Again, say stop there. Make sure that you do something about this. You might want to write down a couple of null hypotheses examples. You might want to look further into it. But crucially, I'd be making something that looks like this in your notes. Again, just a little table that shows you how to do it. Okay? And there'll be a form for you to fill in anyway, where I'm going to make you do a bit of practice.